Electromagnetism 1. Numericals 1, 2, 6, 7, 10, 12 and 14. Electromagnetism 1. An application of Biot-Savart law. Numerical number 1. A circular coil of 500 turns has a radius of 2 meter and carries a current 2 ampere. What is the magnetic field at a point on the axis of the coil at a distance equal to the radius of the coil from the center? Numerical number 1. Given number of turns of circular coil n equal to 500, radius of the coil, that is R, equal 2 meter, and in this case current flowing through the coil I equal to 2 ampere. Distance of a point on the axis of the coil is x, which is a, and here radius is denoted by small a, not by small r. Radius of the coil is small a and the distance x is equal to a. This is the current carrying circular coil. We can draw the axis of the circular coil. A is the radius of this circular coil. A is the radius of this circular coil. O is the center of the circular coil and an electric current I flows through the circular coil, and due to this flow of current, a magnetic field B will be acting at the point at a distance x on the axis of the circular coil. Now the magnetic field induction at a point P on the axis of a current carrying circular coil is mu 0 Ni a square divided by 2 a square plus x square whole to the power 3 by 2, where x is the distance of the point P from the coil, equal mu 0 Ni a square divided by 2 under bracket 2a square whole to the power 3 by 2. Since the distance x is equal to a, means distance x is equal to the radius of the coil, mu 0 Ni divided by 2 into 2 root 2 a, 2 into 2 root 2 a, equal mu 0 equal 4 pi into 10 to the power minus 7 into 500 into 2 ampere divided by 4 root 2 into 2, 4 root 2 into 2. We get the value of B as pi by root 2 into 500 into 10 to the power minus 7. Pi by root 2 into 500 into 10 to the power minus 7. Therefore, the value of B, or magnetic field induction or flux density, is 1110.7 into 10 to the power minus 7 Tesla. Therefore, value of B will be 1.11 into 10 to the power minus 4 Tesla. The value of B, or the value of magnetic field induction or magnetic flux density, is B, which is 1.11 into 10 to the power minus 4 Tesla. This is the value of magnetic field induction or flux density at the point P on the axis of the current carrying circular coil. Numerical number 2. The electron in the hydrogen atom circles around the proton with a speed of 2.18 into 10 to the power 6 meter per second in an orbit of radius 5.3 into 10 to the power minus 11 meter. What magnetic field does it produce at the proton? What magnetic field does it produce at the proton? According to numerical number 2, the velocity of electron is given, which is 2.18 into 10 to the power 6 meter per second. Radius of the circular orbit is 5.3 into 10 to the power minus 11 meter. We have to find the magnetic flux density or field induction at the center of the circular path. P is the center of the circular path and R is the radius, and this is an electron of mass m and charge QE. Electron revolves with the tangential velocity v anticlockwise. in this circular orbit. Electron revolves with the tangential velocity v anticlockwise, and current I will flow clockwise in the circular orbit, and in this case magnetic field induction B will be acting inwards at the center. If the electron revolves anticlockwise with a velocity v, comma, the current produced due to revolution of electron in this circular orbit, it will be I equal charge of electron divided by time period, where charge of an electron is QE, which is minus E. If the electron revolves anticlockwise, in this case with a velocity v, current produced due to the revolution of electron will be I equal QE by T, where the period of time period will be 2 pi r divided by v, and charge of electron QE is minus E. Therefore, will be equal to E divided by 2 pi r divided by V. I is equal to E divided by 2 pi r divided by V, or comma E into V, E dot V divided by 2 pi r, where E is the charge of an electron, V is the orbital velocity of the electron in the circular orbit. I is equal to EV divided by 2 pi r, which flows anticlockwise. This current flows anticlockwise in this circular orbit. Therefore, the magnetic field induction will be B, which is mu 0 I divided by 2R. The magnetic field induction at the center P of the circular orbit B will be equal to mu 0 I divided by 2R, equal mu 0 divided by 2r into EV by 2 pi r, equal mu 0 by 4 pi EV by r square, equal 10 to the power minus 7 into 1.6 into 10 to the power minus 19 into 2.18 into 10 to the power 6 divided by 5.3 into 10 to the power minus 11 whole square. Therefore, B will be equal to 12.42 Tesla. B is equal to 12.42 Tesla. That is the magnetic field induction at the center P of the circular orbit due to revolution of electron. Numerical number 6. A horizontal overhead power line carries a current of 90 ampere in an east to west direction. What is the magnitude and direction of the magnetic field due to the current 1.5 meter below the line? Numerical number 6. XY be a straight conductor and a current I flows from the end Y to X. That means the current flows from east to Y west direction, and P be a point at a perpendicular distance A below the straight conductor XY, and we can denote north and south direction. A is the perpendicular distance. Given electric current I is equal to 90 ampere and the distance of the point P, A is equal to 15 meter and B equal question mark. Magnetic flux density or field induction at the point P below the conductor XY is mu 0 by 4 pi into 2I by A, twice of electric current divided by perpendicular distance, equal 10 to the power minus 7 into 2 into 90 divided by 15. Therefore, B is equal to 120 into 10 to the power minus 7 Tesla. Therefore, B is equal to 1.2 into 10 to the power minus 5 Tesla, which is the magnetic field induction or flux density at the point P at a distance A from the straight conductor XY below, and the point P exists below the straight conductor. And B is equal to 1.2 into 10 to the power minus 5 Tesla. This is the magnetic flux density or field induction at the point P 1.5 meter below the horizontal overhead power line XY, which is placed along east to west direction and this magnetic flux density or field induction acts horizontally towards north pole, horizontally towards south pole, not towards south pole, using right hand palm rule, using right handed palm rule or right hand palm rule. This magnetic flux density or field induction acts horizontally towards south. According to right hand palm rule, if we move our four fingers parallel to current I and turn towards the perpendicular distance A of the point P, then magnetic flux density or field induction B will act horizontally towards south. Numerical number 7. A current of 1 ampere is flowing in the sides of an equilateral triangle of side 4.5 into 10 to the power minus 2 meter. Find the magnetic field at the centroid of the triangle. Numerical number 7. Electric current I equal 1 ampere. Length of each side of the triangle is 4.5 centimeter, means 4.5 into 10 to the power minus 2 meter, and B equal question mark. An electric current I flows clockwise through the triangular coil ACD, and we considered the centroid of the triangular coil. P is the centroid and magnetic field induction B acts at the center P inwards, and B equal to mu 0 by 4 pi 18 I by L, that is the magnetic flux density at the centroid of the triangular coil. B is equal to mu 0 by 4 pi 18 I by L, equal 10 to the power minus 7 into 18 into 1 divided by 4.5 into 10 to the power minus 2, and B as equal 4 into 10 to the power minus 5 Tesla. B as equal 4 into 10 to the power minus 5 Tesla, which is the magnetic field induction at the centroid of the current carrying triangular coil. B is equal to 4.5 into 10 to the power minus 5 Tesla, which acts at a right angle to the plane of the coil and inwards. Numerical number 10. In the diagram we have a combination of two long straight wires with a semicircular coil, and this is the diameter of the semicircular wire, and in the diagram we have two long straight conductors with a semicircular wire. Numerical number 10. In the figure, the curved portion is a semicircle and the straight wires are long. Find the magnetic field at the point O. P is the center of this semicircular wire, and D is the diameter of the semicircular wire, and a current I flows in this direction. An electric current I flows in this direction. Here O be the center of the semicircular wire, not P. O is the semicircular center of the semicircular wire. An electric current flows anti-clockwise through the semicircular wire. And according to numerical number 10, we have to find the magnetic field induction or magnetic flux density, that is B equal question mark at the center O. C is a point on the semicircular wire, and XA is a long straight conductor. Similarly, DY is another long straight conductor. R is the radius of the semicircular wire. The net magnetic field induction or magnetic flux density at O is B is equal to BOXA plus BOACD plus BODY. BOXA plus BOACD plus BODY. Now BOXA is the magnetic field induction at O, due to the long straight conductor XA, and BOACD is the magnetic field induction at the center O due to the semicircular wire, and BODY is the magnetic field induction at O due to the long straight conductor DY. Now in place of BOXA we can write mu 0 by 4 pi I by R, that is the magnetic field induction at O near one of the end A of the long straight conductor XA. Now all the magnetic field induction, that is BOXA, BOACD and BODY, are acting outwards. That's why they are denoted by a dot under bracket. Then in place of BOACD we can write mu 0 I by 4R, plus in place of BODY we can write mu 0 by 4 pi I by R, equal mu 0 by 4 pi 2I by R plus mu 0 by 4 pi into I by R. Now adding the first term and third term, we get mu 0 by 4 pi 2I by R, plus writing the second term as mu 0 by 4 pi into pi I by R into pi I by R. Writing the second term, that is mu 0 I by 4R, as mu 0 by 4 pi into pi I by R. Now taking common mu 0 by 4 pi into I by R, we can write mu 0 by 4 pi I by R under bracket 2 plus pi, where R is equal to d by 2. So we get B as equal mu 0 by 4 pi 2I by d 2 plus pi. Now the magnetic field induction at O due to the semicircular wire ACD is BOACD, is acting outwards. Similarly, the magnetic field induction at O due to the long straight conductor XA is BOXA, which is also acting outwards, and the magnetic field induction at O due to the long straight conductor DY is BODY, is also acting outwards. Now BOXA is acting outwards, that's why it is denoted by dot under bracket. Similarly, BODY, that is the magnetic field induction at O due to the long straight conductor DY, is also acting outwards, that's why it is denoted by a dot. And net magnetic field induction at O due to the three parts, that is due to the long straight conductor XA and due to the semicircular wire ACD and due to the part DY, all are acting outwards. That's why net magnetic field induction, that is B, is also acting outwards. Numerical number 12. A closely wound solenoid 80 cm long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 cm. If the current carried is 8 ampere, estimate the magnitude of B, or magnitude of magnetic flux density, inside the solenoid near its center. Numerical number 12, given length L is equal to 80 centimeter. Length L, that means length of the solenoid L is equal to 80 centimeter. Number of turns of the solenoid, that is capital N, equal 5 into 400, and diameter is 1.8 centimeter. That means radius is 0.9 centimeter, and electric current flowing through the solenoid is I, which is 8 ampere, and we have to find the magnetic field induction, that is B, at a point inside the solenoid. Total number of turns is N, which is 2000, because there are 5 layers containing 400 turns. A cylindrical core on which a wire, an insulated wire, is wound in the shape of cylinder, and this cylindrical coil, or this a coil in helical form, is called solenoid. and this is a diagram of solenoid, and electric current is sent through the wire of the solenoid. Current flows in this direction. N is the number of turns and L, small l, is the effective length of the solenoid. P is a point on the axis of the solenoid and inside the solenoid. The point P exists inside the solenoid. At the point P, magnetic field induction B will act from south pole to north pole. Magnetic field induction or magnetic flux density B at the point P on the axis acts from south pole to north pole. Now, magnetic field induction B is equal to mu 0 Ni equal mu 0 N by L into I equal 4 pi into 10 to the power minus 7 into 2000 divided by 80 into 10 to the power minus 2 into 8 equal 4 pi into 2 into 10 to the power minus 4 divided by 10 to the power minus 1 equal 8 pi into 10 to the power minus 3 Tesla. We get the value of magnetic field induction B as 25.13 into 10 to the power minus 3. Therefore, 2.513 into 10 to the power minus 2 Tesla. This is the magnetic field induction or magnetic flux density at a point on the axis of the current carrying solenoid. Numerical number 14. A toroid has a core non-ferromagnetic of inner radius 25 cm and outer radius 26 cm, around which 3500 tons of a wire are wound. If the current in the wire is 11 ampere, what is the magnetic field outside the toroid? Number 2, inside the core of the toroid. Number 3, in the empty space surrounded by the toroid. Number 14. According to numerical number 14, radius of a toroid, that is inner radius of the toroid is 25 centimeter, R1 equal 25 centimeter, external radius is 26 centimeter, number of turns N equal to 3000, current is 11 ampere, that is I equal 11 ampere, and we have to find magnetic flux density or magnetic field induction at a point on the axis or inside the toroid. So you have to draw the diagram of a toroid. This is the imaginary circumference of the circular toroid. In this case, a solenoid is bent in the form of circle, and a solenoid bent in the form of circle is called toroid. In this case, a wire is wound in the shape of a helix, and that helical coil or cylindrical coil is bent in a shape of a circle. So in this way, a toroid is designed. A wire is wound in the shape of helix, and that helical coil or cylindrical coil or solenoid is bent in the shape of a circle. In this way, toroid is designed. A wire is wound in the shape of helix, and that helical coil or solenoid is bent in the shape of a circle. A current I flows through the toroid in this direction as shown in the figure. P is a point inside the toroid on the circular axis of the toroid. O is the center. At P, magnetic field induction B is equal to mu 0 small ni, where small n is the number of turns per unit length, equal mu 0 into n divided by 2 pi r into I, where average radius or mean radius of the toroid is r, which is r1 plus r2 divided by 2, which is equal to 0.255 meter. Equal, in the next line we can write mu 0 by 4 pi into 2 ni by r equal 10 to the power minus 7. In place of mu 0 by 4 pi, you can write 10 to the power minus 7 into 2 into 3500 into 11 divided by 0.255. Finally, we get the value of magnetic field induction B, or magnetic flux density B, which will be what, magnetic field induction at the point P on the circular axis of the toroid will be B, which will be equal to what? B will be equal to something into 10 to the power minus 3 Tesla. That should be, B will be equal to 3.02 into 10 to the power minus 3 Tesla. Therefore, B is equal to 3.02 into 10 to the power minus 2 Tesla. That is the magnetic field induction, that is the magnetic flux density at the point P on the circular axis of the toroid is B, which is equal to 3.02 into 10 to the power minus 2 Tesla. Now in the diagram, P is a point on the circular axis of the toroid, and at P magnetic flux density or magnetic field induction, that is B, acts tangentially. We can denote the inner radius of the toroid, that is R1. R1 is the inner radius of the toroid. R2 is the external radius of the toroid, and R is the mean radius of the toroid.